All robots all the time.
So first and foremost, the mechanical design. As you can see, the quarter is designed to pick up tennis balls, like I mentioned, and this is the design we decided on. So here is a render of it. This entire robot was designed in SolidWorks, manufactured and made in-house. So you can see here, Velcro belt, tennis balls, and other various components that we'll get deeper into as we go through. Here's a side view of the robot. So first, I want to mention how the robot moves and drives. So there are two drive wheels with a motor here and a wheel, and it's the exact same on the other side. The robot uses tank control. So only one wheel spins, it'll turn to the right or left, and both wheels spin, it'll go forwards and backwards. To allow this motion, there are two casters on the front. Those casters are omnidirectional and allow the robot to move in any direction with very low friction. Casters made of high quality steel, sourced from Dr. Cousin's lab from a previous project. Here's an up close view of those casters and drive wheels. So next, how does the ball actually get collected? So I'm sure many of you are familiar with tennis balls, and they are kind of fuzzy. And that fuzzy kind of reminded us of a Velcro belt, the loop side specifically. So what we have is a conveyor belt made of the hook side of the Velcro that hooks onto the ball and collects it. The ball is driven by a motor at the top, a conveyor, and is deposited into a hopper in the back. It works extremely well, sometimes so well that the balls don't even want to come off the conveyor. So, collecting the ball is just part of it. First, we have to find the ball and locate it and drive to it. So, we do that with a Pi camera. The camera scans the environment, looks for a ball, identifies it, and drives towards it and picks it up. To make sure we don't run into people or objects, we have ultrasonic sensors. Those sensors send out sound in a 90-degree area, and we have 3 on the front, so that covers 180 degrees at the front of the robot. If it sees an object on the left, it will turn to the right. Object on the right will turn to the left. And if all 3 of them go off at once, that probably means something's in front of us will turn around and go a different direction. Like I mentioned, this whole robot was designed in SolidWorks. Every single component was hashed out before being production, so we didn't run into any mechanical problems, and this design took about 2 weeks to make.
Okay, so here's our PyCam for the camera detection. It's almost identical to detecting a Coke can. We use a Gaussian blur, and then I think ours is called like a circle blob to find it, and we use the centroid to determine where it is. We can turn left or right, dead zone in the center, and the size of the circle around the tennis ball determines how far away it is. And if there are multiple balls on the screen, the largest circle is the one it's targeting, and it will ignore the others, so it only draws like one circle. You can go to the next slide. And then we have pathing logic, so it does a random walk if it doesn't see anything with ultrasonics, camera, or 2 line following sensors on either side. If it sees a line on one of the sides that has line following sensors to simulate like the tennis ball court, it stays out of the court area, so if there's a line on the left, obviously it'll turn right, line on the right, it'll turn left. It avoids the inside of the court area to simulate like avoiding the play area during tennis matches practice. Then obstacle detection, it has 3 ultrasonics in front, 1 in the back. If more than 2 ultrasonics in the front are sensed, it just turns around. And it can turn around like on the spot. It doesn't have to go forward or anything thanks to the tank steering casters. If it sees something behind it, it just won't go backwards. It really doesn't back up ever because it can just turn around on the spot. If it sees something on the right, only the right turns left, only the left turns right. So we have obstacle detection there. And then if there are no obstacles or no lines, and it does see a tennis ball, it'll go towards that tennis ball.
Okay, to reiterate our electrical diagram, everything's built around a Raspberry Pi with a motor shield. We have 4 ultrasonics for obstacle avoidance, we have an LED display, and we have 3 motors for main power. This design, however, did not work as the motor shield ended up failing. We aren't really sure why. It could just be a bad part, could be a user error, but we had to redesign the electrical system. This is a simplified version of what we had. We had to not hook up the ultrasonics, so we would have something to test. This one is almost identical to the last one, minus the ultrasonics and the LED screen. However, we ran into issues with this as well, in that our regulator was not able to output enough current to power all 3 motors. It is capped at about 3 amps normally, and we needed about 2 amps per motor to have it function properly. As such, when we ran all the motors at the same time, they tend to stutter and not work properly. Here is the redesigned motor system, with each motor having its own driver and regulator, which worked out much better and functioned as intended. And here's the full electrical system that we used for testing. This is a partially assembled version of it. Motor regulators would be mounted there. However, this image was taken not of the final version. Have our Pi right there. We have our 3 motor drivers there. And then this breadboard acts as a level shifter for our line following sensors. The Raspberry Pi GPIO pins want to use a 3.3 volt signal. However, our line followers output a 5 volt signal. As such, we set up this array of resistors to level shift it down. And this big space on the edge of the electrical board is where our LiPo battery goes.
So the quarter has 13 different 3D printed parts. We mostly utilize the cube, but as you can see, the mounts in the middle, as well as the bearing blocks, they were used with a personal printer just to save on cost and time. The electronics tray, as well as the 2 pulleys and the axles, were printed at the cube using the Ultimaker and ABS material, which gave us stronger parts but still relatively cheap. And then the wheels were printed at the cube using resin printer, and we chose resin because those gave us much stronger parts, and we knew we wanted more strength for the wheels to hold the robot. So looking at our total cost breakdown, the majority came from our in-lab equipment, such as the motors and all of our sensors, motor drivers, and then we did purchasing from Amazon and Home Depot. Amazon, we got line followers and tape to test those. Home Depot was mostly our wood that made up the frame of our robot. And in the end, the total cost came to $488, just under our $500 budget, which we think is reasonable for this product, considering there's one existing tennis ball collector robot that it goes for around $1,000. Here are references. Questions?